Welcome to this walkthrough of LeetCode problem number 147, Insertion Sort List. In this session, we'll explore how to implement the insertion sort algorithm specifically for a singly linked list. By the end of this, you'll have a clear understanding of the approach and its nuances. Let's dive in. In this problem, you are given the head of a singly linked list, and your task is to sort this list using the insertion sort algorithm. Your function should return the head of the sorted list. Now, how does insertion sort work? It operates by iterating through the elements one at a time, progressively building a sorted portion of the list. At each step, one element is removed from the unsorted portion, its correct position in the sorted portion is determined, and it is inserted there. For a singly linked list, you must perform this sorting in place. This means you cannot use any extra data structures like arrays or additional linked lists. Instead, you need to rearrange the existing nodes of the linked list itself. The input to the function is the head of the linked list, where each node contains an integer value within the range of -100,000 to 100,000 and a reference to the next node. The output should be the head of the modified linked list, now sorted in ascending order. Let's look at an example to understand how this works. Suppose the input linked list is 4, 2, 1, 3. The goal is to sort this list into ascending order. Here's how the insertion sort algorithm processes the list step by step. First, we start with the node containing 4. Since this is the first node, it forms the initial sorted portion of the list, which is simply 4. Next, the second node, containing 2, is inserted into its correct position in the sorted portion. This updates the list to 2, 4. The third node, containing 1, is then inserted into its correct position, making the list 1, 2, 4. Finally, the fourth node, containing 3, is placed in its appropriate position, resulting in the fully sorted list 1, 2, 3, 4. Here's another example to illustrate the process. If the input linked list is -1, 5, 3, 4, 0, the sorting proceeds as follows. We start with the first node, -1, which forms the initial sorted portion as -1. The second node, 5, is added to the sorted portion without any changes, making it -1, 5. Then, the node containing 3 is inserted into its correct position, resulting in -1, 3, 5. Next, the node with 4 is inserted, updating the list to -1, 3, 4, 5. Finally, the node containing 0 is inserted into its correct position at the beginning, producing the fully sorted list, -1, 0, 3, 4, 5. For a simpler case, if the input is 1, the list contains just one node and is already sorted, so the output remains 1. Now, let's discuss some important constraints and edge cases. The linked list can have between 1 and 5,000 nodes, and each node's value will be between -100,000 and 100,000. A few edge cases to keep in mind include a single node list, which is already sorted by definition, and a list that is already sorted in ascending order, where no rearrangement is needed. In contrast, a reverse sorted list requires the maximum number of insertions, as every node will need to be repositioned. If all the nodes have identical values, the list is already sorted, regardless of the number of nodes. Lastly, the list can include negative values, so your solution should handle both positive and negative integers seamlessly. These scenarios highlight the importance of designing an efficient in-place sorting algorithm that correctly handles all possible inputs. To tackle the problem of sorting a singly linked list using the insertion sort algorithm, we begin by considering various approaches. A straightforward option is the brute force method, where we convert the linked list into an array, sort the array using the standard insertion sort algorithm, and then reconstruct the linked list based on the sorted array. While this approach is conceptually simple and leverages the familiarity of array operations, it is not well suited for linked lists. First, converting the list into an array and back introduces unnecessary overhead. Second, it requires extra memory to store the array, which increases the space complexity to O(n). Finally, the very advantage of using a linked list, its dynamic structure, is lost in this process. For these reasons, while feasible, the brute force approach is inefficient and not ideal for this problem. A more efficient approach is to perform the insertion sort directly on the linked list, in place, without relying on auxiliary data structures. The idea is to maintain a dummy node at the beginning of the list to represent the head of the sorted portion. Then, for each node in the unsorted portion, we identify where it belongs within the sorted section and insert it at the appropriate position. This process is repeated until all nodes are sorted. The beauty of this approach lies in its alignment with the linked list structure, where inserting nodes at arbitrary positions can be achieved without the need for shifting other elements, as would be required in an array. While the time complexity remains O(n squared), due to the need to traverse the sorted portion for each insertion, the space complexity is a mere O(1), as no additional storage is used. This makes the approach both memory efficient and well suited for the problem. The in-place insertion sort strategy is the most appropriate for solving this problem. The intuition behind it is simple yet powerful. We maintain a progressively sorted portion of the list and insert nodes from the unsorted portion one by one into their correct positions within the sorted section. Using a dummy node at the start of the list simplifies edge cases, such as inserting at the head of the sorted list. This dummy node acts as an anchor, ensuring that the algorithm handles all nodes uniformly. Furthermore, the fundamental logic of insertion sort remains unchanged. It's the implementation that adapts to leverage the linked list structure. Key insights include the fact that linked lists allow efficient insertion and deletion operations without requiring shifts, and that this approach adheres to the problem's constraints while using minimal additional memory. These factors collectively make the in-place approach the most logical choice for this challenge. When comparing the two approaches, the brute force method and the in-place insertion sort, the in-place method clearly stands out. Although both approaches share a time complexity of O(n squared), the brute force method suffers from the additional overhead of converting the linked list to an array and back, along with the extra memory required to store the array. In contrast, the in-place method operates directly on the linked list, achieving a space complexity of O(1). This makes it far more efficient in terms of memory usage. Ultimately, the in-place approach strikes the perfect balance between simplicity and efficiency, respecting the problem constraints and leveraging the dynamic nature of linked lists. It avoids unnecessary conversions, minimizes memory usage, and provides a clean, direct solution to the problem, making it the optimal strategy for this task. In this problem, our goal is to sort a singly linked list using the insertion sort algorithm. Now, unlike arrays, where we can access elements directly using indices, linked lists require traversal to access specific nodes, which adds an extra layer of complexity. The challenge here is to implement the insertion sort algorithm directly on the linked list, without converting it into another data structure. To clarify, the task is to rearrange the nodes of the linked list so that they are in sorted order, while ensuring that the relative order of duplicate values remains unchanged. Key constraints to keep in mind are that the input list can contain up to 10,000 nodes, and the values in these nodes can be positive, negative, or 0. Insertion sort works by processing one element at a time and inserting it into its correct position in the sorted portion of the list. For linked lists, this requires careful manipulation of pointers to reorder nodes efficiently. To begin implementing the algorithm, we first initialize the necessary pointers. We create a sentinel node, also known as a dummy node, with a value of -infinity. This dummy node serves as the head of a new sorted list and simplifies edge cases during insertion. Next, we use a pointer called current to traverse the original list, starting from its head. While traversing the list, we process each node one by one. For each node pointed to by current, we temporarily store its next node in a variable called next_node. We then detach the current node from the original list by nullifying its next pointer. The key operation here is to find the correct position for the current node in the sorted portion of the list, which is anchored by the dummy node. To do this, we use another pointer called previous to iterate through the sorted portion. This pointer helps us identify the position where the current node should be inserted. Once we've identified the insertion point using the previous pointer, we proceed to insert the current node into the sorted portion of the list. This involves updating the pointers. We set the next pointer of current to point to previous.next, and then update previous.next to point to current. This effectively places the current node between previous and previous.next. After completing the insertion, we move the current pointer to the next node in the original list, which we had stored earlier in the variable next_node. This process is repeated for every node in the original list. Once all nodes have been processed, the sorted list is fully constructed, starting from dummy.next. At this point, we return the pointer dummy.next as the head of the sorted list. This marks the completion of the insertion sort algorithm on the linked list. There are a few key insights that help us understand the algorithm better. First, the use of a dummy node is critical. It simplifies the insertion logic, especially for edge cases where a node needs to be inserted at the very beginning of the list. Without the dummy node, we would need additional checks to handle null pointers and other special cases. In terms of efficiency, the algorithm has a time complexity of n squared. This is because finding the insertion point for each node requires a traversal of the sorted portion, which can take up to n in the worst case. Since this operation is repeated for all nodes, the overall complexity becomes quadratic. While this is manageable for small to moderate input sizes, it can become a bottleneck for the upper limit of 10,000 nodes. On the positive side, the algorithm is space efficient, requiring only 1 extra space. This is because we directly manipulate pointers without creating any new nodes or auxiliary data structures. The algorithm relies heavily on the structure of the singly linked list and the dummy node. The singly linked list is manipulated directly to reorder nodes, and the dummy node plays a vital role in simplifying edge cases during insertion. Speaking of edge cases, there are several scenarios to account for. If the input list is empty, meaning the head is null, we simply return null immediately as there's nothing to sort. For a single node list, no sorting is needed since the list is already sorted, so we return the node as is. Another scenario involves lists where all nodes have the same value. In such cases, the algorithm still works correctly because it preserves the relative order of nodes, which aligns with the problem requirements. Finally, we should consider the case where the input list is sorted in descending order. This represents the worst-case scenario for the insertion sort algorithm, as each node will need to be compared with every other node in the sorted portion before finding its correct position. This results in the maximum number of comparisons and pointer adjustments, reinforcing the n squared time complexity. Despite this, the algorithm remains a straightforward and space-efficient solution for sorting linked lists, particularly when the input size is small or moderately large. Here, we begin by defining the list node class, which represents the nodes in our linked list. Each node has a value, val, and a pointer to the next node, next. Then, we move on to the solution class, where the insertion sort list method is implemented. This function takes the head of a linked list as its input and sorts the list using the insertion sort algorithm. We start by handling a couple of base cases. If the list is empty or has only one node, there's nothing to sort, so we simply return the head. Next, we add a dummy node at the beginning of the list. This dummy node helps simplify edge cases, such as inserting a new node at the start of the list. We initialize two pointers, prev_sorted, which tracks the last node in the sorted portion of the list, and cur, which points to the current node we're trying to insert into the correct position. The while loop then iterates through the list as long as cur is not null. Inside the loop, we first check if the current node's value is greater than or equal to the value of the last sorted node. If it is, the node is already in the correct position, so we simply move both prev_sorted and cur forward. Otherwise, the current node needs to be repositioned. To do this, we detach it from the list by updating the next pointer of prev_sorted to skip over cur. Now, we need to find the correct position for this node. To locate the correct insertion point, we use another pointer, previous, which starts at the dummy node. We traverse the list with previous until we find a node whose value is greater than or equal to the value of cur. Once the correct insertion point is found, we insert the cur node by updating its next pointer to point to the node after previous, and then updating prev next to point to cur. With this, the cur node is now in its correct place within the sorted portion of the list. Finally, we move the cur pointer to the next node to be sorted, which is now the node immediately following prev_sorted. The loop continues until all nodes have been processed. Once the sorting is complete, we return dummy.next, which is the head of the newly sorted list. This implementation ensures that the list is sorted in place, making it both space-efficient and easy to understand. Here, we begin by defining the structure of a singly linked list through the list node class. This class has three constructors, one for an empty node, one for a node with a value, and another for a node with both a value and a reference to the next node. This flexibility allows us to create linked list nodes in various ways. Next, we implement the insertion sort list method, which takes the head of a linked list as input and returns the head of the sorted list. The first condition checks if the list is empty or has only one node, in which case no sorting is needed, so we simply return the head. We then introduce a dummy node with a value of 0 to simplify insertion operations. This dummy node points to the head of the original list, and it acts as a placeholder to streamline edge cases like inserting at the beginning. Finally, we initialize prevSorted to the head of the list, which keeps track of the last node in the sorted portion of the list. Now, we define cur to represent the node that we are currently evaluating for sorting, starting with the second node in the list. The main loop iterates through the list as long as cur is not null. If the value of cur is greater than or equal to prevSorted, it means the current node is already in its correct position within the sorted portion, so we simply advance both prevSorted and cur. However, if cur is smaller than prevSorted, it indicates that the current node is out of order. To reposition it, we first remove cur by adjusting the next pointer of prevSorted. Then, we search for the correct insertion point for cur by iterating through the node starting from the dummy node. We stop at the node immediately before the position where cur should be inserted. After finding the insertion point, we adjust the pointers to insert cur into its correct position. Finally, we update cur to the next node to continue sorting the rest of the list. At the end of the process, the dummy node's next pointer will point to the head of the fully sorted list. By returning dummy.next, we ensure that the sorted list is returned without including the dummy node itself. This concludes the implementation of the insertion sort algorithm for a singly linked list in Java. The algorithm maintains its efficiency for small lists and ensures stability, meaning that nodes with equal values retain their original relative order. The use of a dummy node simplifies the handling of edge cases, making the code both cleaner and easier to follow. Let's begin with the input list, 4, 2, 1, 3. We start by creating a dummy node with the value 0, which will serve as a placeholder to help us with inserting nodes into their correct positions. Initially, the prev_sorted pointer is set to the head of the list, pointing to the node with the value 4, and the cur pointer is set to the second node, which has the value 2. In the first iteration, we compare the value of cur2 with the value of prev_sorted 4. Since 2 is less than 4, we identify the node with value 2 as out of order. To fix this, we remove the node with value 2 from the list by updating prev_sorted.next to skip over cur and point to cur.next, leaving us with the list 4-1-3. Next, we need to find the correct position for the node with value 2. Starting from the dummy node, we iterate through the list until we find a node where the next node's value is greater than 2. In this case, we insert the node with value 2 between the dummy node and the node with value 4. Our list now looks like dummy-2-4-1-3. Finally, we update cur to point to prev_sorted.next, which is the node with value 1. Now, moving to the second iteration, the cur pointer is at the node with value 1, while prev_sorted still points to the node with value 4. We compare cur.val, which is 1, with prev_sorted.val, which is 4. Since 1 is less than 4, the node with value 1 is out of order. To remove it, we update prev_sorted.next to skip over cur and point to cur.next, resulting in the list 4-3. Again, we start at the dummy node and look for the correct insertion point for the value 1. We iterate until the value of the next node is greater than 1, and we insert the node with value 1 between the dummy node and the node with value 2. The list now becomes dummy-1-2-4-3. Next, cur moves to prev_sorted.next, which is the node with value 3. In the third iteration, we compare cur.val, which is 3, with prev_sorted.val, which is 4. Since 3 is less than 4, the node with value 3 is out of order. We remove it from the list by updating prev_sorted.next to point to cur.next, leaving us with just the node 4. This time, starting at the dummy node, we find that 3 should be inserted between the nodes with values 2 and 4. After performing the insertion, the list becomes dummy-1-2-3-4. Finally, cur is updated to prev_sorted.next, which is now none. The sorting is complete, and the final sorted list is 1-2-3-4. Now let's consider a different example with the input list 1, 2, 3, 4. As before, we initialize the dummy node with the value 0 and set preb_sorted to the head of the list, pointing to the node with value 1. The cur pointer is set to the second node, which has the value 2. In the first iteration, we compare cur.val, which is 2, with preb_sorted.val, which is 1. Since 2 is greater than or equal to 1, the node with value 2 is already in the correct position. Therefore, we simply move preb_sorted to point to cur, and cur is updated to cur.next, which is the node with value 3. In the second iteration, cur.val is 3 and preb_sorted.val is 2. Again, since 3 is greater than or equal to 2, the node with value 3 is already in the correct position. We move preb_sorted to cur and update cur to cur.next, which is the node with value 4. Finally, in the third iteration, cur.val is 4 and preb_sorted.val is 3. Since 4 is greater than or equal to 3, the node with value 4 is also in the correct position. We move preb_sorted to cur, and cur is updated to cur.next, which is now none. Since the input list was already sorted, the final output remains unchanged as 1-2-3-4. For the final example, we have the input list 3, 1, 2. As usual, we create a dummy node with the value 0, set preb_sorted to the head of the list pointing to the node with value 3, and set cur to the second node with the value 1. In the first iteration, we compare cur.val, which is 1, with preb_sorted.val, which is 3. Since 1 is less than 3, the node with value 1 is out of order. To address this, we remove the node with value 1 from the list by updating preb_sorted.next to point to cur.next, resulting in the list 3-2. Then, starting at the dummy node, we find the correct position for the value 1. We insert it before the node with value 3, giving us the updated list dummy-1-3-2. Next, we update cur to point to preb_sorted.next, which is the node with value 2. In the second iteration, cur.val is 2 and preb_sorted.val is 3. Since 2 is less than 3, the node with value 2 is also out of order. We remove it from the list by updating preb_sorted.next to point to cur.next, leaving us with just the node 3. Starting at the dummy node, we determine that 2 should be inserted between the nodes with values 1 and 3. After performing the insertion, the list becomes dummy-1-2-3. Finally, cur is updated to preb_sorted.next, which is now none. The sorting process is complete, and the final output is 1-2-3. Here, we're analyzing the time complexity of the insertion sort list function. The total runtime depends on the number of nodes in the linked list, which we denote as n. First, the outer while loop processes each node exactly once, as the cur pointer moves sequentially through the list. This contributes an O(n) term. Now, for nodes that are out of order, the algorithm uses an inner while loop to locate the correct insertion position. The number of iterations in this inner loop depends on the size of the sorted portion of the list, which starts at one node and grows to include all k-sorted nodes as we progress. For the worst-case scenario, this means the inner loop runs for one iteration for the first node, 2 iterations for the second node, and so on, up to n1 iterations. When we sum these iterations, we get the formula n1/2, which simplifies to O(n²). This quadratic time complexity is the worst-case runtime for the insertion sort algorithm applied to a linked list. Now let's break this down further into 3 different scenarios. In the best case, the list is already sorted, so the inner while loop doesn't run at all. The outer loop simply traverses the list once, resulting in a time complexity of O(n). For the average case, the inner loop will typically traverse about half of the sorted portions nodes on each insertion. While this reduces the number of comparisons slightly, the overall behavior is still dominated by the quadratic growth of the total iterations, making the average case time complexity O(n²). Finally, the worst case occurs when the list is sorted in descending order. In this situation, every node must be compared to every previously sorted node, causing the inner loop to reach its maximum iterations for each insertion. This leads to the quadratic time complexity of O(n² that we calculated earlier. The space complexity of the insertion sort list function is O(1), as the algorithm operates directly on the input list without using additional data structures. Let's break this down. First, the sorting is done in place, meaning the original linked list is modified directly to produce the sorted result, so no extra space is allocated for a separate sorted list. Second, the algorithm relies only on a constant number of pointers, such as dummy, prev_sorted, cur, and previous, to track positions within the list. Lastly, there's no recursion or auxiliary storage involved, which further ensures constant memory usage. This efficient in-place sorting is what keeps the space complexity at O(1). To put things into perspective, let's compare this optimized approach with a brute force solution. A naive method would involve creating a new linked list and inserting each node from the original list into its correct position in the new list. While this approach would still have a time complexity of O(n²), due to repeated traversals, it would require O(n) additional space to store the new list. In contrast, the optimized solution we're analyzing sorts the list in place, reducing the space complexity to O(1), while maintaining the same time complexity. The use of a dummy node is a key improvement here, as it simplifies edge case handling, such as inserting at the start of the list. To summarize, the insertion sort list function involves two nested loops. The outer loop runs n times, and the inner loop runs up to n times in the worst case, yielding a total time complexity of O(n²). The space complexity remains at O(1), making this an efficient solution for sorting linked lists. When working on the insertion sort for a linked list, there are several common mistakes to watch out for. First, failing to handle edge cases, like an empty list or a single node list, can cause issues such as null pointer exceptions or incorrect outputs. In these scenarios, your function should simply return the head of the list as there's nothing to sort. Another frequent oversight is not keeping track of the tail pointer in the sorted section of the list. Without a reference to the last sorted node, reconnecting the unsorted portion becomes challenging and can lead to broken list structures. Additionally, pointer updates during the insertion step require extra care. With singly linked lists, forgetting to update the next pointer for the previous node or overwriting the next pointer of the node being inserted can result in infinite loops or lost nodes, which makes debugging particularly tricky. Finally, modifying the original list head directly without utilizing a dummy node is another pitfall. This approach can complicate scenarios where nodes need to be inserted at the beginning of the sorted section, making your implementation less robust for edge cases. Now, another issue to consider is the inefficiency of searching for the correct insertion point. Scanning the sorted section repeatedly for every insertion results in O(n²) complexity, which can be a bottleneck for larger lists. To improve performance, look for opportunities to break out of the search early when the insertion point is found. From an interview perspective, this problem is a great way to demonstrate your understanding of sorting algorithms and how they can be adapted to linked list structures. It's important to show that you recognize edge cases, such as lists with 0, 1, or 2 nodes, and that you can handle duplicate values gracefully. You should also be ready to discuss trade-offs, such as why insertion sort is a natural fit for linked lists due to the ease of inserting nodes, compared to arrays where shifting elements is more costly. Lastly, you can highlight the optimal space usage of your solution, as it operates in place without requiring additional memory, which is often an important consideration in coding interviews. To further strengthen your understanding, it's helpful to explore related problems that involve similar concepts. For instance, LeetCode 21 focuses on merging two sorted linked lists, which is a common subroutine in sorting algorithms. Another relevant challenge is LeetCode 148, which asks you to sort a linked list in O(n log n) time, typically using a merge sort algorithm. LeetCode 206, which involves reversing a linked list, is also highly relevant as it emphasizes crucial pointer manipulation skills needed for insertion sort. Finally, LeetCode 2, which deals with adding two numbers represented as linked lists, provides another opportunity to practice traversing and modifying linked lists. Tackling these problems will deepen your understanding of linked list operations and pointer management, equipping you to handle a wide range of scenarios effectively. There are also alternative approaches and trade-offs to consider for sorting linked lists. One straightforward option is the brute force approach, where you convert the linked list into an array, sort the array, and then reconstruct the linked list. While this simplifies implementation, it increases space complexity to O(n), and sacrifices the advantages of working directly with linked list operations. Another option is to use merge sort, which is a divide-and-conquer algorithm that achieves n log n complexity. Merge sort is faster for larger lists but requires additional implementation effort and can consume more memory due to the recursive stack space. Lastly, if the list were doubly linked instead of singly linked, insertion sort could be further optimized. The ability to traverse backward would allow quicker identification of the insertion point, reducing the time spent searching. However, this modification changes the problem's constraints and increases memory usage due to the additional pointers in a doubly linked structure. Each approach has its advantages and trade-offs, so the choice depends on the specific requirements and constraints of the problem. Great job completing this problem. To summarize, we tackled the insertion sort list problem by adapting the insertion sort algorithm for linked lists. We covered its time and space complexities, the key implementation details, and when this approach shines. Thanks for tuning in. Don't forget to like, share, and subscribe for more coding tutorials. Until next time, happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!